See, this is my talk is on the photonic. I thought, I'll pick up this topic so that it would be useful for the young students, who would be starting their work and probably in the area of optics, nonlinear optics, and so on. Or optoelectronics. Practically, optoelectronics is also a very good area. Here, before I go to the photonic crystal stuff, actually, I thought, because there are a large number of students the young students are there, maybe for their sake, I thought I can pick up few topics which I thought, one particular topic in terms of, what a simple white light can do. Okay. What kind of studies that we can obtain? See, because I always tell my students, young boys, see, your kitchen and living room are the best teachers in your life. Okay, if you observe very keenly the stuff that is going on in your kitchen, right from the Bunsen burner. Okay, I mean, why it is color is blue, why is it not red, how it is becoming blue. I mean, about surprising that 90% of our even our PhD students do not answer why the Bunsen flame is blue. Right? I mean, because there is so much of science in it that we have to understand. If we learn the science, then we know what is the kind of an interaction between the different, how the combustion takes place and how the heat is coming and so on. So there is a lot of, also the tube light. Okay, does the tube light have an anode and cathode? Okay, we don't. I mean, many people will say no. And you take the plug that we put a socket inside one, we know what is the kind of, whether you have got, which is the phase, which is a neutral, whether the neutral carries more current, whether the phase carries neutral more current. All these questions are very, very interesting. And there is a lot more science that one can understand and learn from it. So that's why my first slides will be, I wanted to go back into my the elementary BSc stuff. Before I come to my photonic crystal studies, I wanted to just talk about this stuff. This is a simple biprism experiment which every one of you, every one of us actually have gone through several times, and sometimes the students struggle hard. Okay, where when you consider they have a source and you have got the fringes, or they don't see the fringes. One of the tough experiments. You take a sodium lamp, you put because the trouble is they don't know how to adjust the source slit width, and they will be struggling hard to get the fringes onto the screen. It becomes very difficult job. Of course, ultimately of struggling, accidentally or something like by adjusting the slit to a narrow portion, and then probably they will see the fringes. Okay. Now, and only they simply use the formula beta is equal to lambda t by d, and then calculate what is the source wavelength and so on. Okay, that's the typical job that one does. Now, here this interesting thing is what this lambda that is doing here. What is the lambda function of the lambda, right? Okay. Now, lambda, I suppose if in the case of sodium light, okay, you have 5890, 5896, two wavelengths which are very, very close by. So they don't really contribute to the really two fringes, but there will be a single fringe. Unless somebody has got a good monochromator set inside a fringe, they would be able to see two fringes, right? Okay. So now, whereas if you go to a white light, okay, what happens in the case of a white light? So this is what you see. Suppose here, actually, I have taken a fringes, which is a green source. Doesn't matter whether it is a sodium light or green source, it is a monochromatic source. And then you will see a nice fringes, okay, which is the bottom one. And the top one, you see the fringes that you will see with a white light, right? Okay, now this is very, this is very, very interesting to observe, because when I joined my lab in 1990, I was given a room by Professor Agarwal and said, this is your room, this is the lab, your lab, and you have to start working on it. And I came from one of the best labs in the US, Professor Prasad lab, where, we had about 3 or 4 femtosecond lasers, and we were working with all femtosecond laser systems. So coming back here, we had to struggle hard. So I thought, okay, we picked up this problem. That is the time when Professor Wolf also published his Wolf shift. So we thought, okay, we will try, let me try with this white light. That is how they set up. And when you look at the fringes, the central white fringe looks very bright white. You don't see the much color. Okay. And you will see after dark, you just keep observing. So, okay, that you start bluish color. And then as you go towards more towards the left or right side of the central fringe, you will see red color. Again, blue appears. And then, so then after further distance from the center, you will see all the colors become merge. Okay. So probably here this photograph shows only a small distance, but if you go further distance, again they all become smeared. You will not see a patch of colors. You will never see any color also. It will just look like a faint white light. Okay. Now, so the question that everybody should ask is, why the white light is getting separated into different colors? Why the red light is far than the blue portion, and why the central fringe white light, and so on. Okay. So this is what actually this initiated. Okay, this is what we did, and then we implemented it in our MSc students. They did enjoy this one. Of course, we gave a job for them to develop measurement of the refractive index of a thin film. They also did that one using a biprism. You can do a fantastic work with that one, measurement of a thin film, refractive index, and so on. Suppose then what we did was, we thought we wanted to explain, because what happens when the white light is like it's a diverging beam, the collimating is really difficult. So what actually we developed an incoherent laser light source, which is like you just take a green 532, pump a dye laser. Okay, you see now dye is if you call it as laser, what is a laser? Laser is nothing but, okay, it has got large number of round trips. Depending on, say, like a nitrogen laser, you have maybe a couple of round trips are good enough for the lasing gain to achieve. For example, helium neon is a low gain system. You may require 30 round trips or 40 round trips or 60 round trips to have a perfect gain. That's why you have got the mirrors also designed in such a way that the gain of the system, okay, more gain is required, then you have got a high reflectivity of the mirrors, and so on. Okay, so now in case of this broad band, where suppose we reduce the reflectivity of the mirrors, then you will have only 1 or 2 round trips. Then what happens? You get a collimated beam. Okay, but still the beam is not a coherent source. It is a very spectrally broad, right? It's very spectrally broad. Then that means you have got which permits you to do large number of experiments. So you have a laser. It's not a laser. It's an incoherent source, but it has got the one of the properties that we always mention, that it is a collimated beam. That is what all it has got, is that collimation, nothing more than that one. Okay, because it has got emission. This is a dye where you can see the emission from 570 to 590, right? Okay. So that is the spectral width of the laser, and then you make them interfere. You get suppose in the Michelson interferometer, or you can use the Mach-Zehnder interferometer, whatever interferometer that you want to use. Okay, you displace them small amount. You see the same whole color. If you see spectrally on the screen, it looks like the same color. But if you disperse it with a spectrometer, you will see a beautiful fringes, just like the one. So now these fringes, what we call it is the spectral interferometry. This is what actually is. So that means your white light is the same thing. Suppose if you go to the white light, you can suppose you get same thing. You can see white light is almost right from the 400 nanometers to 700 nanometers. You see the spectrum. So you can adjust the path difference between the two arms of any of your interferometer, and then you will see a beautiful fringe pattern, which actually the fringe pattern is actually depicts that of the your path difference between the two. If the path difference is too large, then you will see you come back to your original the light source like this. Okay, if you are very close, you will see large. You will see. If this is a small difference, delta path difference is very small. As you increase the path difference, you see large number of phases. Of course, this is a blue region, because you can see the blue region spectral interference is very fast because omega is very high. compared to your IR region, right? That becomes, you know, like, I mean, what actually I wanted to put it in is, see, because it's we talk about Raman. Raman is I mean, I consider him one of the greatest really scientists. I mean, he had a beautiful observational skills. Actually, probably many of us would have probably neglected, that is some stray light that we have seen on the anti-stoke side. But this person, because of that eminence is appears there, that he did not say that, oh, that is some kind of a wrong signal that he is seeing, but it is something that, you know, like that you see, that you see it because that he wanted to investigate, and of course he got the Nobel Prize because of that one. Okay, right? So this is how this is how that one is came. So this, in terms of the white light has got a large amount of potential. If you see that one, actually, I can almost 3 of my students worked on the white light only. Nirmal, who is also a professor now, Venugopal, who is also a professor now, Marti Manoj is also a professor now. Okay, at IIT Kharagpur. So they are all worked on simply using the white light source. See, you can see the put, you know, like if you put, you can see this is a spectrum where you can see the 2 peaks. One is the red side, one is, if you adjust such a way that, you know, you can see the 2 peaks. If you put a photodiode, one in the blue side and one in the red side, and if you take the difference in the voltage output, then you can have a perfect switch. You don't need anything. Actually, this was the starting point of, you know, like, I mean, singular optics, which has become now so popular. The optical vertices and so on. So you have got, you know, now the phase is, you know, like at the center is I mean, because you have got a singularity, you create a singularity by you with your own the spectral difference. Okay, that's what actually you have got. You see that is what you can see. Okay. Now, actually, I wanted to ask you, if any of you want to disturb me, please, you can stop me there. Is it okay? Hello.
Okay, sir.
Anybody, you know, like, who wants to disturb me and stop? Want to ask question, because it's not like a, I mean, I don't consider it like a lecture kind of a thing, but I want it like should be more like a discussion. If you want to stop me, please stop me, and then I can go ahead. Okay. Yeah.
Is this singularity similar to what is shown in the vortex beam?
Yeah, almost singular. But you are now purposefully creating that kind of a singularity here. Okay, so singularities is not exactly that vortex beam, but it's even vortex beams are also created, right? Okay. Through phase modulation. Here also you are practically creating the phase modulation. Okay, yeah. So this is practically okay. So see, because when I put the screen, I'm not able to see the people, so that, you know, if you can stop me in the question, then I will stop it, because I'm seeing only the screen. Okay, not the question or raising hand. Okay, right. Okay, now this is a very this is something that, you know, like, I mean, even now we are studying this one. Actually, we try to develop a system which is a portable system using this kind of a thing. I mean, this is very important, you know, like for optics people. See, when you write the electric field of the electromagnetic wave, what you write E is equal to E naught into e to the power of I omega t minus k dot r, right? That is what we write. See, now the k dot r is a very, see, now when the light passes through any medium, a thin film or so actually it goes through a refractive index medium, which is a complex function of both dependent on the wavelength as well as the thickness. Okay, the delay. So now unfortunately for optics people, the degree of difficulty is that your k dot r. So that means 2 pi n by lambda into x or z, whatever you call it, and then you have got, you know, that means your n and x are multiplied, right? So that means if you make an error of delta x in your thickness, you are actually making a delta n error in your refractive index measure. So that means they are not. See, just one single experiment does not give a perfect value of neither your n nor your x. You can go to nanometer resolution, nanometer accuracy, but because your N and L are product in your phase term, okay, you will never be able to, you have to have two particular systems, two experiments where you are, unless you know exactly precisely my N is this, and then only you can measure my X or del, okay, or you have, if you know my thickness very precisely, then I can measure. Okay, this is the uncertainty that is there. So to have uncertainty, actually what you have, you can have always, you can go for the reflectance. See, reflectance is simply proportional. Your R is proportional to your delta N variation, right? Yeah. Now you will see my slide. Okay, this is a cover page of Jonah Police, the book, the first book that he wrote on the photonic crystals. And that he has given, and if you look at this picture, it's the imagination of how your optoelectronic system should look like. Okay, this is your model. Okay, so your photonic, your waveguides, your everything, like directional couplers and so on. So the couplers, so you both nonlinear elements. You can think of any element. You can have all the elements possible in this circuit. That is how he thought about and put it as a cover page. Okay. Now, okay. And you look at the, one of the great scientists, what a great scientist, Albert Einstein quotes are very beautiful. If you go through all his quotes, you really love them. Look deep into nature and then you will understand everything better. Okay. See, this is what actually took almost 1987 before, your Sajiv John and your Yablovich could come out of the photonic crystal structures. But until 1987, nobody thought about, the photonic crystal structure. But it was there in the nature all through. Okay. So you see the butterfly, you see the structure. If you look at, the same picture of the butterfly, okay, you see a beautiful nanostructures, okay, which actually reflects large different colors, beautiful colors. So also the feather of your the peacock. So then you can see such a beautiful colors, intricate colors, how it is organized. Okay, nobody could. So now, of course, people have tried to see the cross section. Now the people try to understand, and that's how it is coming up. See, this is a opal structure, another naturally occurring kind of a thing. Okay, so this opal structure also, it's a beautiful, is a natural formation. Sometimes the opal is more expensive than even your diamond. Okay. So the opals, just nothing but a silica with, silica with, beautiful with H2O as, a component inside the system. Okay, so that's how they form the beautiful silica different structures, and then they reflect different colors. These are the naturally occurring photonic crystals. Of course, both the great scholars, Sajiv John, okay, and then Yablonowicz, of course, they have been nominated for the Nobel Prize, and we don't know if they get, probably we'll be very happy. One more Indian getting the Nobel Prize. Okay. And I'm sure they would get it for the amount of work that has been going on in this direction. See, if you look at the now the photonic crystal, now you have to actually, there is a one question to the young people. Okay, a crystal. You see, if you look at a crystal simply, okay, I am trying to bring an analogy of the photon with the electron here. Okay, a crystal, if you take, it's a simple periodic arrangement of an atoms or molecule. Okay, and if, of course, which results, when the basic building block is repeated across, X, Y, and Z direction, then you have got a three-dimensional system. Okay, so this is what actually you see, the electron, because of, experiences, periodic potential at every point of these atoms or the molecules, and due to the Bragg diffraction, you get, it propagates along some directions and forbidden to propagate in other directions. Okay, and other energies also. Same also with the energies. Certain energies can be propagated in certain directions. Certain energies are not permitted to propagate in certain directions. Okay, so if you have got a strong potential at these points, then you get a complete band gap. Okay, like for example, semiconductor. Semiconductor has got a band gap depending on what is the kind of germanium, silicon. Their band gap varies into different materials. They have a different band gaps. Okay, so now the photonic crystal. Now I have to bring an analogy. Now, how do we bring an analogy with respect to the electron experiencing this periodic potential? Now, how does the photon experience this periodic potential? Right? Okay. Now that's a question mark. Now here I have to ask you, ask some young people a question. Now, what is the difference between electron and the photon? Okay, now suppose just imagine you electron, you treat it as a wave, right? Okay. So now if you treat it as a wave, right, because it has got its own rest mass, and if you calculate de Broglie wavelength, it comes out to be around approximately 0.1 angstrom. Because of that reason, now you have got a wave from the electron, which is actually that of like around that 0.1 angstrom, which electrons get diffracted inside a crystal. So whereas photon, which is, if you take around green, which is about 500 nanometers, which is much larger than this atomic spacing, right? Is it not? So your atoms are about 1 angstrom apart in a simple crystal. So this wavelength of light is about 500 nanometers, which is too large for that, practically 5,000 times, 5,000 angstroms, which is 5,000 times. So that means they don't see any periodic potential. They have the envelope sees as if like a uniform material. So it doesn't get light, doesn't get diffracted. So now, if you want to artificially create this potential, so what do you have to do? So you have to bring this periodic potential into the scale of your optical wavelength, right? So which is about few hundred nanometers. So that means your photonic crystal has to be artificially created with a material which has got a periodicity of here. That's why they are all called, most of the photonic crystals are artificially created, except that are there which are available in the nature, right? Right. So we said, because the propagation of certain energies are prohibited in the for the electron in certain directions. So also here in a photonic crystal, if you can light a matchbox outside, but if you take a perfect photonic crystal, if you can create a perfect photonic crystal, and if you want to light a matchstick inside that photonic crystal, it will never light, because photons cannot exists or it cannot come out. So it will be always dark. So you can never light a match inside a photonic crystal, right? So this actually gives rise to indirectly an idea that, oh yes, if I have an excited energy, that means it is going to remain there for a long period of time. It cannot come down. So that means, you can actually practically create a metastable state and make the lasers much more efficient. That is actually the concept of our advantages of your the photonic crystals. Now if you take photonic crystals, now you have got large number of varieties. Now for the elementary one is like a one-dimensional photonic crystal, so where that means the periodicity repeats in only one direction. Here you have taken along the horizontal direction, so you have two different refractive indices, n1 n2 repeating in the one direction, whereas the same the repetition in the 2 dimensions, it becomes 2D photonic crystals. And if you have the periodicity is in 3 dimensions, then it becomes a 3D photonic crystals. Okay, this is what actually you practically need here. So now, if that means that practically what you see whatever you learned in your condensed matter physics or solid state physics, okay, actually you can bring it into your electromagnetism, and then you see you practically view your photon like an electron. Okay, the same analogy, whatever you see there, you apply over here, right? Okay. So that means just like like a lattice plus basis your crystal structure. So now if you say A1, A2, A3 are your basis vector for crystal, Okay, then you have reciprocal lattice, you have got your B1, B2, B3, okay, which is a reciprocal lattice, like a lattice vector becomes G, whereas in a real lattice vector, your R. This is a standard, your the condensed matter, you go to the kettle, you will have exactly, it's all from the kettle book only, so you will get these are these three. So now your UVW and HKL are the integers in your regular lattice, real lattice, and reciprocal lattice. Okay. Now this is a simple. I don't want to go through this one because this is simply you talk about the Brillouin zones, because Brillouin zones becomes very important. Because you want to look at the propagation of the K vector. Okay. Now the propagation of K vector, which is R, you talk about the energy. Okay, propagation direction in the energy. That's why your Brillouin zone becomes, the reciprocal lattice becomes much more important than the actual real lattice vector. So that's why you create a reciprocal lattice, and look at you create a first Brillouin zone and so on, so forth. For you are trying to create the first Brillouin zone. Okay, how to create the first Brillouin zone is exactly you take a bisectors of the nearest neighbors. The line joining the nearest neighbors, that whatever is the center, like here, whatever this the first Brillouin zone, like in the case of square lattice, you have got a different Brillouin zone. So this is the kind of a thing, and then you try to solve you go back to your standard electromagnetic wave equations. Okay, for the mixed dielectric media, and then write the wave equations. Okay, this is your master equation is exactly the same as you go back into your Schrodinger equation. You derive exactly the same way, the same analogy, whatever you have followed in the quantum mechanics. I don't have to go through because you are all experts in this one. You are fresh with one. Okay, so you write in the equation in terms of the magnetic field. Okay, so there, if you look at the becomes this Hermitian eigen solutions, which will happen only with your eigen state is the magnetic, like magnetic field H. Okay, rather than like your rather than your E. When you write the same equation in the form of a E, then you will never the operator which you had seen earlier. Okay, it is an eigen operator. Here for the E, it doesn't become an eigen operator. So normally that's why that's what you do. You solve this equation, okay, for allowed state for any kind of suppose you have to create your own. Suppose you create a photonic crystal, let us say, which are separated by 200 nanometers, 300 nanometers, okay, with a sphere diameter of like let us say 10 nanometers, 100 nanometers, 200 nanometers. Okay, you create your own the three-dimensional potential function. Okay, evaluate your the eigenvalues. Okay, and then you derive from there. Once you derive the H, from that you derive the electric field function. Okay, that's how you try. Whereas because if you go the other way, it doesn't work. So now this is how you try to come out with the permitted the eigenstates are. So that is what like that means so that means just like your K versus the energy. Okay, you get the K versus omega, whatever your energy or omega. So you get the permitted energy states in a different directions, right? Okay, I will show you what the band diagram, how you get the band. Just like you remember your kettle work, it exactly looks like that one here. Okay, so to be frank, I'll come back. Okay, it's just it's your K versus your E. So you whatever is this is the energy curve that you derive it through your the master equation. Okay, there are different solutions, different. It's a plane wave approximation method is there, density functional theory is there, you have finite element methods is there, finite different time domain. So they have several methods are there to calculate this energy band diagram, which are now I can sometimes RSoft is also there, where you can calculate very easily this band diagram. Okay, you get different band diagrams, different functions. This is the lowest two, so you can get in the higher states also, higher energies permitted states also. Okay, so now when you come to the, so I will talk about only one-dimensional photonic crystal and three-dimensional photonic crystal. Not the type where 2D is also very important for communication purpose, for optoelectronics purpose. Okay, but I will skip that one because for us much more easy for manufacturing both 1D and 3D. That's why we concentrated on both 1D and 3D. Okay. See, 1D is how do you create 1D? So you take a substrate, you have a low index material, and then you have got a high index material, low, and high refractive index materials. So if you have various index materials, so that means, you along X and Y directions, it is practically uniform, and along the Z direction, you have got, the where the index varies. Okay. So that's how it is. So now if you look at the reflectivity of this photonic crystals, it is a simple standard solution. You don't need anything. Simple mathematics, you take N1, N2, okay, and then you calculate the reflectance from the surface and multiply with the large number of layers that you have got. Okay, that's what your reflectivity is going to be, R. Okay, so the simple, very simple solution, which is basic, like actually it comes from your the high school or the first year BSc stuff. So now the maximum reflectivity is going to be coming around with 2 beta is equal to m5. Okay, or your product of N2 H2 is going to be, or the thickness is going to be m lambda by 4 cos theta 2, or Nd is equal to lambda by 4. That means provided you have got lambda by 4, okay, you achieve the maximum reflectivity. Similarly, when you have two layers of two different refractive indices, so that's okay, before that one, I can show you this reflectance, like you have got a number of layers, or the different layers, different number of layers, and then the total reflectance. See, what happens if you have got best reflectance comes out, okay, when you have a higher refractive index contrast. That means n high, n low should have maximum contrast difference. For example, 2.3, 2.4, and another one is about 1.6, 1.5. You will have a very good reflectance. Okay, so also your band gap structure is going to be one. So that's why, like the P is the number of layers that you have. If you calculate, you will see that whenever you have got a high refractive index difference contrast, you will see a beautiful refractive index. When you have two layers, that means now you see you have got each layer is lambda by 4. Okay, that means prior to my making the film, I have to know what is the refractive index of that particular material. I evaluate and then see that my product N1 T1 is lambda by 4, where suppose I want to create a photonic crystal at 532, so that means my lambda is 532 by 4. Okay, right? N1, so it's same thing by N2, N2 D2. I have got N2 D2 is the same way. That means, right? Isn't it? Okay, so that means I have create N1 D1 lambda by 4, N2 D2 as lambda by 4, it can be lambda by 2. So then I will have a perfect photonic crystal which is getting. Okay, so now you see around this one, all the photonic crystal, it just rejects all the light around this one. So now if you want to look at it, what is my width of the photonic full wave half maximum width actually depends on of course my difference between the the high and low refractive indices, right? That's correct. Okay, so that is how you have my delta lambda. That's all. This is symbolically a calculated one. If you can see the transmission of how the reflectivity, this is a transmission, so reflectivity is the other way. Suppose now if you look at the band gap, okay, this is the transmission. Okay, now if you do you see what makes big difference is the index difference, not the number of layers. You see, index difference for the red curve, it is the index difference is only 1.0, whereas the index difference for this blue curve is about 0.3, but the number of layers are 14. So it makes a big difference what is the best the index contrast that you can get it when you make a photonic crystal. Okay, now people will ask where the band gap is coming from. Okay, this is suppose you take a uniform crystal, so that means my epsilon is equal to, that means dielectric constant is the same at all places. So irrespective of my A, so that means epsilon x is equal to epsilon x plus A, that means my dielectric constant is the same, which is a uniform material. If I take a uniform material, the two solutions from the energy wave from the same solution with your master equation, one is a sine and another is a cos function. Okay, you have, because it's a constant, both of them merge at, if you can see, both of them merge at the same point. See, there is no difference between the two. Okay, but the moment you introduce a small change in the dielectric constant, delta epsilon, okay, then what you see that means, I have got epsilon 1, which is higher than epsilon 2 by a delta epsilon. Okay, again, but it is periodic. What I see at the k, which is nothing, pi by a, okay, you see there is the degeneracy gets split. So now cos pi by a x, because it's a higher refractive index, your n is larger. Okay, so that means it's going to be, n is going to be larger. So you have got it's much lower, and then your the upper state is n is lower. Where that means it's a it's a slightly, the degeneracy gets lifted. So that is how the band gap forms. Now this what people call complete band gap, or band gap in the narrow directions. Okay, see, complete band gap is something like diamond. Diamond has got a band gap in all different directions. Okay, so now if you to create such kind of a thing, people have struggled a lot. I will. I mean, people. Yeah, even Yablonowitz actually tried to create kind of a diamond kind of a structure, which will come how he tried to do that one. Okay, but to get a, I mean, one of the most difficult job is to create a complete band gap. So that means band gap in all different directions. That is going to be very, very tough. Okay, why it is tough? That means you can see the nature has like its own laws, and it could create because the atoms could be arranged in a particular direction, whereas you cannot arrange the spheres or the balls that you create. Physically, you cannot arrange in a particular direction. The people have tried different techniques. This still is an art. It is a just open area. People struggle hard, come up with the different methods. I mean, that's a way to. I mean, that's what the science is never ending. It's always there. Okay, now you also try to see if you have like you try to you have got now what happens like this is what we call ultimately this lambda by 2 structures that you have created, lambda by 4 structures that you have created, nothing but act like your original Bragg mirror. Okay, people said some people are working in fiber Bragg gratings. It is nothing but inside a fiber you create a periodic density changes, variations, or the refractive index variations, so which acts like a Bragg mirror. So you have one Bragg mirror on one side and you have one Bragg mirror on the side. I can create a small cavity which is lambda by 2, where I can suppose if you look at the kind of the plane wave method and calculate what is where my energy density is going to be there, you see that you will see that your all the field major concentration is going to be in the defective states. Okay, this is called actually this is original like Yablonowitz paper, which is again published in 1987 in the world. So that is what actually they were the defect mode. The one. See, this is what actually our structures where we have created SiO2, TiO2 structures. Okay, so because you have got refractive index variations are there, you have got TiO2, like refractive index, because you take the TiO2 refractive index and then both of them, you calculate lambda by 4, looking at the refractive index of these mirrors, which comes lambda by 4 comes approximately 195 and another 210. Okay, and of course the half wave layer becomes 490 nanometers. Okay, right? Okay, now you look at this. I mean, the stuff depends. Like what you have. This actually we tried for in the IR valence. Okay, for the communication valence, which is about 1545. So you can see that there is a because this defect transmission becomes at what. So of course, if you make a very good one, the defect transmission can go all the way to 50-60%, 70%, which you will see it in the another state. Okay, these are the TEM images. Okay, suppose in the same, you can different type of quality. So you can defect layer, how perfectly you can make it. you get that kind of a high quality factor. You can increase the quality factor up to 90 also. Very good, 90, 100, much higher than, like a very good high quality factors, you can increase it. Okay, so this is your band gap. Okay, and then your defect. Of course, now if you see the defect layer, which is appearing around, let us say, whatever wavelength appearing, but if you change the direction, if I rotate my direction, of course, you can change, you can also move the defect in that particular direction, because you have got energy propagation, permitted energy propagation is in a different energy. So naturally, you can move, it is not a fixed one, it's a direction dependent. Okay, so that means this defect is whatever state you have, if you could, because that's what actually our energy band diagram shows, right? So if you change the different directions, so that means the propagation direction changes. Once the propagation direction changes, my energy permitted frequencies also changes. So that means I can control, because it's a thin film. Okay, all the thin films coated on a glass plate. Okay, so I can vary almost like 70 degrees angle, so I can move this one anywhere from this end to this end. Okay, within the band gap I can move it very, very well. So that gives the versatility for the operation. Okay, you don't have to worry that, oh, I have calculated and it has formed here, somewhere here, but I can always move it by looking in the direction that I look at. Okay, we will see that some of the results that we show. One, see, when you come to the 3D stuff, this is which like what originally called it as Yablonovite structure. This is if you see that Joanna Police book, you will see the same picture. This is picked up from that book. Okay, actually he created this Yablonovite structure. Okay, by drilling holes in a medium in a 3 different axes, which is almost like 35 degrees away from the normal and 120 degrees. Okay, you 3 axes, you drill holes, you create a Yablonov. So this actually gives, this is called a Yablonovite structure. Okay, so this gives, it's a complete photonic band gap structure. If you take 100 direction, okay, you will not get a perfect band gap. But if you go 110 direction, that is where your photonic band gap. You see by creating the holes in a particular sector, you get a good FCC structure. Okay, which gives rise to this photonic band gap throughout. In whatever direction that you see, that means the energy gap within this region is completely, photons are prohibited in this region. Okay, whatever here is 0.5 to 0.6. Okay, suppose if you are not creative, if you don't have FCC structure, if you have another one, probably this is the energy level, so maybe it comes down. So then you will be left with only this much band gap in other directions, they will be touching, right? So that means you don't have, let's say somewhere else, if you create different type of structures, these energy levels may be degenerate here, that means there is no band gap there, right? So you have band gap only in a particular direction, but not in the other directions. So these represent, like you go back to solid state, like you see the gamma identifying the center, X is one particular direction, W is in the direction. Okay, so that means, like you have got, so it depends, like 0.100, 110, 111. So it depends on X, L, and K. These things differ, identifying the different directions. Okay, so whatever may be the different directions, that means you have got a band gap in that particular direction. That is the beauty of the photonic crystal. Now, how do you prepare a opal preparation? Okay, see, opal, you have seen the natural opals, right? It's a silica, naturally formed silica. Okay, here, how do you prepare an opal? See, now you take here,
Narendra sir.
Yes, yes.
1 minute.
Yes, yes.
You require mode restrictions, for example, T mode, TM0, or only TEM00 mode?
No, you can TM also is help. Yes, you can create the photonic band gap both in the TEM00 and then TE00 mode. You can create, because when you calculate, depending on it is a structure which defines what is it the mode that is permitted.
Okay.
So that means size and the direction. You see, because you see that FCC is going to be band gap for both TEM and TEA.
Okay.
TM and TE both.
Okay.
Depends on the like what is permitted energies. Okay. So you can calculate.
People normally use laser beam. That's what I'm asking.
Yes. Yeah, actually you can create, because the structure created. You see band gap. See, now RSoft gives you very easy to calculate these band gaps. Okay, you don't have to go through all the struggle. Okay, you can simply calculate, but you have to create your own structure. Okay, this is the structure I'm going to have.
Okay.
Okay. See, now what becomes difficult in this scenario is to represent. That's why, like I want to quote, the another the Einstein one. You see, to create replicating nature sometimes it's very difficult.
Yeah.
Okay. So, but what we do, but we have to succeed in doing that one, right? So, your FCC structure is so difficult to create an FCC structure.
Yeah.
Okay. How do you create in the tetragonal symmetry like a diamond? How do you create the balls oriented in A? No way, right?
Yes.
Okay. You require some kind of a physical contact method so that I can keep ball. So the only way that you can keep
scattering effects, scattering and absorption effects also will be there, right? So
that is your quality of your photonic crystal is going to fall down. See, the moment you have absorption, scattering is always there.
Yes.
Actually, scattering is the one which is responsible for your directional emission.
Yeah.
If there is no scattering, okay, there is no crystal structure at all.
Yeah.
Right? Because it is scattering, which is you're directionally allowing light to go in a particular direction.
Yes, correct.
Whereas absorption is a killing. Absorption, if you have an absorption, your photons are being reduced into the matrix. Right? Okay. Yeah. So now you see, this is like like people see that you some of you like when you go some balls, their children will be playing with the balls. If you see the balls, tennis balls, small balls, like children, they'll be playing. If you look at the balls, they're all placed in one, like in a particular fashion. If you one above the other. Okay, if you do that one, that's it. It's not FCC. It's you have got what you'll see is the 110 plane. That actually the plane that you see, all the balls. You shake them, all the balls put together and shake them. They all arrange it like one. The ball's center. You say 100 direction. Okay, that's what exactly it happens. Suppose if you I take like the polystyrene balls. Okay, polystyrene beads, small beads, which is about 200 nanometers or something like that. Okay, or 300 nanometers, where I want to create my band gap, right? So we're choosing 200, 100, 300, 400, 500 depends on my choice of the lambda where I want to create. You can create anything. These days, like actually, I would prefer you synthesize at home or synthesize in your own lab is much better than buying commercial. You can buy the commercial one. People buy it commercially, but it never works good. Okay, my own experience is that if you synthesize it, because they're fresh materials, what happens? They are not what happens? Surface gets deformed or hygroscopic. Okay, they all get contaminated. So it will never be the same as but you prepare. It's much more easy to prepare synthesizing the polystyrene beads in the lab. Okay, if you struggle hard for a couple of months, you will succeed. Okay, but that is the one. So you can suppose just imagine. Let us imagine with a commercial set, suppose 200 nanometers, and then you can put them in a the beaker with whatever water. Okay, and then just keep a substrate, and then let the water evaporate. Then you will get a simple photonic crystal structure. That's all. Nothing more. Just let it evaporate. But you have to monitor the temperature and exactly precisely. What happens if the temperature is more or less? What happens? The evaporation is faster or slower. Depending on that one, you will never have the uniform crystal structure. So creating a uniform crystal structure is really, you have to master it. Everybody isn't suppose my student does it and I will not be able to reproduce the same way like my student does it, because he follows meticulously. He has to observe how he is doing it, right? Okay, that is what actually the photonic crystal, this is one kind of a thing. Of course there is a beauty. Another way of doing it is called the lithographic technique. See, if you take if a photoresist SU8 is there, people must have used SU8. SU8 is very common. If you want to create a photonic crystal, in the IR beam, okay, I will tell you why. SU8 I have tried. I tried for 1 year to master the SU8 in the visible region. See, what happens if you use the visible region, the grating spacing is going to be of the order of, few hundred nanometers. Okay, now when you have few hundred nanometers, see the wall thickness is going to be very, very, very thin, right? Once wall thickness is very thin, see the structure, if you look at the structure, see the wall thickness is so small, okay? It just, like a few nanometers thickness. Now, this is nothing but SU8, okay? Such a small thickness, what happens, it collapses. The whole thing collapses by its own weight. Okay, so you will not be able to really sustain. But if you go to the same thing, you create in the IR region. So let's say 1.5 microns, 1.5 microns, which is the communication wavelength. You can do it, SU8. You don't have to struggle hard with the polystyrene beads. You can actually create a beautiful photonic structure with a 3-beam. This is nothing but, like Yablano white, where you drilled holes in 3 different directions. Here you send the 3 beams, laser beams in 3 different angles, exactly same angles. That is 35 degrees and 120 degrees in the azimuth. So that means you create that kind of a that holographic grating. The SU8 gets polymerized, okay, and then where unpolymerized regions you dissolve it. Okay, then you get a photonic crystal structure. Beautiful one. For 1.5 microns, it's very, very easy. But coming to the visible region, it is going to be damn difficult, But one has to struggle hard. Okay, that is how the synthesis of the 2 technique that we have followed. One is the layer by layer cohesion, which is the RF sputtering system. One is then of course, you don't have to have RF sputtering system also. If you can do actually, if somebody is very smart enough, you can go to the sol gel preparation technique. Sol gels are, you can create the sol gels of silica and titanium sol gels, a particular, layer by layer reflect. But that's really an art. Okay. Some students would be very good, some students would be, they can never succeed. Okay, sol gel once you can, like for example, one of my students, Shivakiran, who is in right now, who is in IIT Kharagpur, he did an excellent job. But another student tried and he failed. He could never succeed. Even after working for 1 year, he could never succeed. So it depends on, how meticulous, how careful you are in terms of working with sol gel. But sol gel is a beautiful one if you can succeed, because you can create on a large area. Okay, so that means if you want to screen, you have to 1 meter by 1 meter, you can create with sol gel, but you can never do it with the sputtering method, right? That is the advantage of sol gels. Okay, now I will try to see some of the, how much time I have got? Professor Sankaraman, how much time I have got? Professor Sankaraman, anybody?
Yes, sir.
How much time I have got?
Oh, we can finish 10 minutes, sir. 10 minutes more.
10, 15. Okay, fine. Okay, fine. No problem. Okay. I will see now. What happens is I'll just look at some applications. Okay, that's what actually will do it. Okay. See what for any transition. See the number of states. Like the number of states. Like you see, for any transition, you look at the density of states. Okay. Okay, the transition rate is proportional to the density of states, like Bachara. That's what we want to create, the density of states. That's why, if you look at this graph, okay, see the bulk, the density of states, like as a function of energy, you can creep on, it monotonously increases. Whereas if you go to the quantum well, a 2D structure, and then a quantum wire, and then quantum dot, you see the density of states, like with a very narrow energy gap that you have. So this is where actually in India we have to do the perfection is developing these quantum dots, like in a perfect quantum dot, uniform dot of dots. Okay, a same size beading. See, that's where actually the India, though we are preparing a lot of quantum dots, but we are not able to make it uniform size. That is one of the biggest difficulty. Okay, this is silicon. Okay, this is a photonic crystal. See how the same structure. If you see silicon diamond structure. Okay, how difficult is it to arrange it in terms of the diamond? There is no way that you can arrange it in a this kind of a structure. Okay, right. So now you see the density of states, like as the frequency increases, you can, the number of states that increases, it goes as omega squared. Okay, and then for a 2D structure, it goes by omega and so on. Okay, this is the simple number of states. But one of the very important point that I want to bring it out here for the photonic crystal is, you just look at this photonic band gap diagram, right? See, this is the lower end, which is in the high index medium. This is the low index medium. Okay, this is called what? That's why we call always this kind of air band. This one we call it a solid band. Okay, right? High density. So that means because the whole energy curve, the energy is inside the dielectric medium. This is inside the low refractive index medium. So that's why we call it the air band. Okay, right. So now, but if you look at here, okay, this is a flat curve. Okay, that means this is a flatness. So now, now if you look at this is the one, the group velocity, if you look at it, d omega by dk, it turns out to be 0. That means, there is a group velocity is 0. That is where you talk about, like that means I can reduce the group velocity to 0. That means, like what I'm trying to do is I'm slowing the light. Okay, and because of that one, I will have a beautiful light matter interaction. Right? Okay, this is how where the energy. This is, I told you, air band and dielectric band. The dielectric band and this air band. Okay, because the energy is concentrated in where the energy is concentrated, that defines the band structure. Right? Okay. Now this is the same. No, this is our people calculating. Like density band, you can calculate very easily. This is not nowadays. It's very easy. Okay. Now I come to one of our beautiful results that one or two results that we have got. Okay, this is the inward silica we created. Inward silica is this pure silica, the silica matrix. Okay, sorry, polystyrene matrix. So now you incorporate silica inside that one. Okay, diffuse silica inside that one, and then you heat it, thermally heat it up, evaporate your pure polystyrene. So then you will be left with the silica matrix. These are all holes. Now earlier it was filled with solid polystyrene solid. Now these are holes. Okay. Now you have got a pure silica matrix. Now with the silica matrix, you can actually infiltrate, the amino. You functionalize with amino groups. Okay, and then you can incorporate, because you see, and then you incorporate gold or silver, whatever particle that you want. Okay. Now I have a matrix embedded with the gold or silica, gold or aluminum. You couldn't have done this one here because your gold, the particles wouldn't have penetrated. Okay. Whereas inverse silica, because you have holes, it takes all this one. So now this is the one which we have created. Suppose you see here all the silica matrix, embedded with your practically your gold particles. Okay. This is a inverse silica opal. Okay. So that means open, but it's the inverse of it. So the inverse opal is because much more popular when the studies. Okay, now we try to look at, like we try to do the Raman, and then you see beautiful Raman is, like this is your band gap to photonic crystal. This is this is due to your surface plasma absorption peak. Okay, right? So now because now what you have got, like when you look at, the kind of a Raman. Okay, now you see Raman with a pure, like this is a ISO inverse silica opal with benzene thiazole. Okay, and whereas this is on a gold film and this is on a photonic crystal. You see there's a beautiful enhancement into the Raman signal. That is because this is, you have got both surface plasmonic as well as photonic reflect. That means you have got reflectivity is very high. Also your effect of plasmonic structure. That is what actually it looks at. But you see there is another one which when you try to record it, you record, you see 632, 785 and something. But if you look at the Raman should be strong with 5145 compared to your 632. But here it shows very weak. That is because, you see, whereas if you put in a gold film, it exactly follows the regular Raman scattering, omega to the power of 4. So that is because omega is smaller here, it is weak, becomes stronger and strongest with 5145. So what is the magic that is happening is that, if you look at the band diagram system, okay, 5145 falls on the, okay, 5145 falls. See, this is the high energy side. This is, remember, this end is the high energy side. This is the low energy side. Reason? So this is lower frequency side. This is the higher frequency side of the band gap. So lower frequency side, naturally it will be in the on the dielectric medium. So dielectric medium, which has got all plasma, right? You are all metal. So that means, you know, that means you have got, you know, you see much stronger because the field, that means it's a beautiful, where the field is confined is very, very obvious when you look at here, or when you compare to the 5145. So that means you can create, I mean, your own band structure, such a way that you can actually control the scattering, whatever way you want scattering, you know, where you want to enhance it. So there's a beautiful physics that you can do with this kind of a phenomena. Okay. That's what, you know, these are all, you know, like creation of one, you know, how the energy is in the air bands, how the energy is concentrated in the lower field with 632. It's all confined in the dielectric medium, because dielectric medium is one attached with your the thiazole molecule, so that's where it experiences maximum field. Okay, that's what it is. Okay, so the same thing. It's exactly the same stuff which we did, you know, when we did with this one. We thought, okay, we'll go for much simpler one. This is a simple, you know, how you create a multi-dielectric medium, you know, photonic crystal structure with a RF etching. Okay, so this is etching with current source. In the silicon, you can etch it and create a beautiful porous silica structure. Depending on the porosity, I can control its refractive index. Right. So this is how I can control. I can see this is a beautifully controlled refractive index. Same image shows in a beautiful structure. Okay, I can use the same way that I can use the Raman studies, which is immaterial. Okay, so you can see how my field is confined. Okay, these are all transfer matrix simulation methods where I can see that my field is confined in the defect layer, and I can look at, you know, how the Raman enhancement and so on. Okay, that's a simple Raman studies. You know, I don't care about looking at that one. Okay. Yeah, see, we wanted to demonstrate, you know, like how well is the pure. See, the same concept, you know, the same concept in a polystyrene swirl gel. We create 532 with a nanosecond laser. You see, the red layer. When I change the angle, that means I will be tuning my band gap. By tuning the band gap, I will be, you know, I have for the red, you know, it falls on the lower frequency side. That means actually I'm sitting onto the material, so which constitutes a good 2-photon absorption. So that means I see a strong 2-photon absorption onto the material. But when I move it to the other side, both at 5 degrees, 15 degrees, 30 degrees, and 40 and 50, I do not see that one, because the field falls onto the other region side. That is actually the way that I can create, you know, into the one. Okay. This is the one actually we try to do. Actually, the Cochin University has done a lot of work on in terms of your the zinc oxide. Okay, we try to look at the zinc oxide. Okay, zinc oxide, they have done, you know, a strong 2-photon absorption. We wanted to do that one same thing here in a photonic crystal. See, this is on a thin layer of same thin layer which we have kept it in a separately on a glass plate. Okay, and this is the one which is inside the defect, λ/2 layer, inside a photonic crystal. Okay, see the enhancement in the order of enhancement. You know, it's a beauty. It gets, you know, completely. I can use a very lower power, and the inside a photonic crystal, I can achieve the. I mean, with a much little material, I can achieve the same results as in terms of the good multi-photon absorption. Okay, this we try to demonstrate. It has got large number of applications. That, you know, of course, we have tried to show that, you know, it's a glass plate, how beautifully a very thin layer of few microns will act like a good photonic crystal. Okay, there are a lot of, you know, because since you people are good in the optoelectronics division, and then you can demonstrate, you know, like a 2D structures, you can create a directional transmission, or you can have a coupler. This is where, you know, you can, if you take a nonlinear medium here, if you can inject nonlinear medium into the one, you can actually able to couple light into the from one channel to the other channel. So that means optical switch. So I can have a nanosecond pulse here. You can demonstrate beautifully in a simple coupling. This two-dimensional structure is creation is not difficult at all. Okay. You can create, you can actually simplest method, you know, I told you right in the beginning itself, you know, you have to come out with the innovative method where I can create this layer, I can create a polystyrene, I can remove it, and so on. So there are so many ways of, we can discuss that one with your students. Okay, and then you can do the simple coupling of light. So I can have an optical switch. Okay, you can demonstrate that optical switch also. I mean, people, LED emission, these people have demonstrated, of course. Okay, optical bistability still is a workable problem. Many people have demonstrated a good optical bistability. Okay, but we can still do the optical bistability, which is, if you imagine that two reflectors, Bragg reflectors, and then which is confined, so you can have a good bi-test reflector. Okay, of course, supercontinuum is demonstrated, is now, it's like a workhorse in the generation of supercontinuum. And there is another one. See, before we actually 8 years ago, we were supposed to do the super lens and super prism. That is what one of our project. But since I retired, so we could not complete super lens and super prism. Super lens is something that where you can either focus within about few microns. See, even you are much better than your 90 magnification lens that you use in the microscope. And super prism is something that you want to diffract light. Okay, the prism has got, even if you take refractive index prism of 1.5, you cannot refract light that well. But super prism here, you can get almost 80 degrees of angle between the two lambdas. That means, let us say, red and blue, which is phenomenal. Of course, negative refraction you can achieve. You can umpteen number of. See, one has to be creative in creating any kind of an application. Slow light. So these are the some of the great applications that it has got. Potential is very high, and I thank you people for having a patient listening.